to you.
Okay, so am I audible at the back? So I am Sukhdeep from IIT Kharagpur. I will talk about the effect of peculiar velocities on epoch of reionization bispectrum. So, inferring from cosmological principle, universe is on large scale statistically homogeneous and isotropic. So that means the statistical properties of the statistics of the underlying field distribution is translational and rotational invariant. Okay. So on the left hand side, in the left panel, I have shown a isotropic H1 distribution, typical distribution. So any statistics of that field, for example, power spectrum, is rotational invariant. Okay, so if we want to find the power spectrum corresponding to this K mode, so it does not depend upon the orientation of K mode in that field. So we call this the real space, which is isotropic. However, when we observe any field distribution in the universe, there is additional anisotropy introduced due to the peculiar velocity of these tracers along the line of sight direction. So this effect is called the redshift space distortion. On the right hand side panel, I have shown the field, the same distribution with redshift space distortion introduced. Okay, so you can see the distribution, the underlying distribution here, it is isotropic in approximately, but here some clustering patterns along the line of sight are produced. Okay, so if we want to find the statistics of this field, for example, power spectrum again, so the power spectrum will depend upon the orientation. So this K mode, the power spectrum corresponding to any K vector will depend on the orientation of this K mode, and this effect of anisotropy and or the effect of rotational this rotational effect of this K vector is quantified using this mu. So which is the cosine of angle between line of sight direction and the K mode we are studying. Okay, so here you can see the so if any distribution, for example, if it is a matter distribution, if it is a spherical overdense region, it is spherical overdense region, then we will see it as a squashed along the line of sight direction, and because the here along the line of sight direction it is squashed, but on, the effect is zero on the right hand side of this, like here, which is perpendicular to the line of sight, and here effect is zero. So this mu, which is the cosine of angle between line of sight direction and the K vector, is used to quantify the effect of this redshift space distortion. So in previous studies, the effect of this redshift space distortion on power spectrum has been studied extensively. So one of this study is done by Dr. Shuman Majumdar here. So the power spectrum, so this effect of redshift space distortion can be studied by decomposing the redshift space power spectrum into this Legendre polynomial. Here, this PL mu is the Legendre polynomial, and this PL, which is the coefficient of expansion in the this Legendre space, is called the multipole moments. So they have studied the monopole, which is L is equal to 0 pole, and quadrupole, L is equal to 2, and L is equal to 1 pole will be 0 due to so there is a still symmetry on the plane perpendicular to the line of sight. So now the question we are addressing here is what is the effect of this peculiar velocity on bispectrum. So bispectrum, as introduced earlier, is the ensemble average of three fields corresponding to three different K modes, which are forming a closed triangle. Okay. So basically bispectrum is the function of any closed triangle configuration, and we will study what is the behavior of bispectrum corresponding to different uh, triangle configurations. And here, similarly, as we have seen in previous power spectrum, so because the bispectrum depends is the function of 3 k vectors, so we have to consider 3 different angles with respect to line of sight that should quantify the behavior of orientation of the triangle. Okay, so it turns out similar to the power spectrum, the effect of redshift space distortion on power spectrum can be quantified by decomposing the redshift space bispectrum in spherical harmonic basis. So this is the expansion of this function power bispectrum. Here K1, K2, K3 are different modes correspond to, and P represents the orientation of the triangle. So this BLM we call the multipole moment, and this YLM is the spherical harmonic corresponding to some orientation of triangle. Okay, so the components of this P can be related to mu1, mu2, mu3 that we have introduced earlier. Okay. So to show the results of bispectrum, so as it depends on the orientation, on the shape and size of the triangle. So we have taken the parameter. So we can take any parameterization of bispectrum. For example, 3 sides of triangle or any 2 angles, 1 side, etc. So we have taken this parameterization where this K1 is the largest side of triangle. Okay, so K2 is the second largest side of triangle, and K3 is the smallest side of triangle. Okay, so one of the parameterization is the largest side of triangle. Second is the mu, which is the cosine of angle between largest and second largest side of triangle, and third is the T, that is the ratio of second largest to largest side of triangle, and we will use this. So you have to pay attention to these parameters. Okay, so the advantage of taking these parameterization is as follows. So if we can show the bispectrum as the previous speaker has shown in mu t space. So in mu t space, we can see all the possible triangle configuration can be seen here. Okay, so for example, this is mu from 0.5 to 1. This is T from 0.5 to 1. So this corner corresponds to equilateral triangle. This is L isosceles squeezed, and this is linear. This is the stretched triangle, and so this is the right angle triangle, and this is S isosceles triangle. So we will not go to details. So now what we have done is we have run the simulation using Re-ion Yuga and generated the H1 field, and these are some parameters of if someone is interested. So this is the cube we have taken 215 megaparsec and grid and the minimum halo mass and okay, and we have taken generated this data corresponding to 6 redshift from redshift 13 to 7 in a single okay. So and we have taken 45 realizations of each redshift, and we have also generated data for real space and redshift space. Okay, so this work has been done by Suman Parmanik here. So this is typically the what we have generated to show you that for increasing redshift, how epoch of reionization progresses. So we have studied the real space bispectrum. So for real space bispectrum, the only component is a monopole, and for redshift space, we have studied only 2 poles: monopole moment, which is L0 M0, and quadrupole L2 M0. Okay, so this is the study we have done. So the similar study has been done by Dr. Majumdar here, and so they have taken only 1 realization and compared with some models. So also they have studied the monopole. Okay, so how I have done this thing. So the bispectrum that can be decomposed into spherical harmonics. So for m is equal to 0, the spherical harmonics just boils down to your legendary polynomial. Okay, so so we can find these multiple moments corresponding to m is equal to 0 as this. Okay, so this is the your bispectrum in redshift space, and this is the legendary polynomial. And by taking the average over different triangle orientations, we can find the different. So we can find the multiple moments corresponding to different triangle orientation, different triangle configurations. And second thing in our study is the important thing is, as cosmic variance is directly inversely proportional to number of triangle configurations we are taking. So as we take more and more number of triangles in some corresponding to some bispectrum configuration triangle, so the cosmic variance drops down. So this is a typical mu-T space diagram. Here, one point corresponds to one triangle configuration, as I shown before. So we can do binning in mu-T space, and this binning we do in such a way that the signal to noise ratio is significant, so that we can, so there is a hope to detect the signal corresponding to that. So first of all, the results for real space bispectrum. So these are the results for these plots are correspond x-axis is the redshift. So as we go from left to right, the epoch of reionization progresses, and so this result is for equilateral triangle. This is for stretched triangle, and this is for squeezed triangle. So the non-Gaussianity, so the bispectrum. So if we see here, so bispectrum in the magnitude of bispectrum increases here as we go as reionization progresses, and the maximizes somewhere and then again starts decreasing. Okay, so first here it is also important to note that, so here the sign of bispectrum corresponding to so here the sign of bispectrum is positive, and then it changes sign. Okay, and then again it starts decreasing and changes sign for some k values. Okay, so these so this change in sign is very important, as Dr. Suman Majumdar has said that. So the negative sign of bispectrum here corresponds to that the non-Gaussianity is driven by the H1 field, and if bispectrum is positive, then non-Gaussianity is driven by the matter fluctuation, underlying matter fluctuation. Also, the non-Gaussianity is large at small length scale here. So non-Gaussianity is, so here you can see corresponds to this stretched triangle that so this is for large k values. So non-Gaussianity is high, and so this is the typical diagram for mu-T space. So here each panel, so as we go from, so each panel is a mu-T space. As we go from left to right, the time progresses, or the value of z decreases. So this is for z 13, 11, 10, so on. And as we go from above to below, so the k values increases. Okay, so this is for small k1, and this is for high k1 value. So for small k1 value, so there is a negative sign in middle and largest. So positive at the Z13 and 7, and the values of that bispectrum is higher at squeezed limit. And so here also as we increase k value, so the values of bispectrum becomes positive at linear limit here at the higher value of mu, and the overall magnitude goes on increasing. Okay, okay, so the bispectrum increases with K1 as the larger modes become sensitive to small H2 regions as epoch of reionization grows. So this is the signal to noise ratio. So so signal to noise ratio corresponding to each bin. So for most of the region, the signal to noise ratio is very high. Okay, for some regions where bispectrum crosses 0 from negative to positive, so here the signal to noise ratio drops. Okay. So for redshift space, the monopole, similarly, uh, the bispectrum here, sorry, okay, increases the the monopole here these results are for the bispectrum redshift space bispectrum monopole, and these are for the real space. So this is just for comparison. I could have shown you the ratio of these two, but uh, so, so so this is what I have right now. So so the redshift space distortion increases the magnitude of bispectrum basically, and sometimes the sign also changes. Okay, so here the magnitude is for example 6 times greater here, or somewhere for squeeze limit it's also 10 times higher, and also the sign is also very important. For example, for this uh, k mode, here the sign changes in between, but here for due to redshift space distortion the sign does not change. So this is the muti space. So as k increases, more mu t space becomes positive. So in real space, so the one point I would like to highlight is that for a real space, this was the negative for less mu values. But as k increases, the more and more uh, values uh, in the linear limit becomes positive, and at the higher k1 value, this the bispectrum corresponding to this k value becomes positive entirely. Okay. So this is the reason that the nonlinearity is more prominent at the small length scale, hence the effect of redshift at large k is more. So this is the so for the for okay. So for quadrupole, so these are the results for quadrupole. So the error corresponds to quadrupole is very high, and the bispectrum also is positive in most of the region here, and we are we have not yet studied this results, and we are discussing how to analyze these results right now. So okay, so this is the uh, muti space results for quadrupole. So here the main thing to note is that so in small k1 or at the larger scales, we had to take entire muti space as one bin to detect the signal. Okay, so otherwise the signal to noise ratio is very small, and for higher k1, so we have divided this entire muti space into two bins, and for highest k1 values, so we have divided it into 8 into 8 binning scheme. So here you can detect the quadrupole signal very much, but on smaller k1, so the detection is very hard. So this is the signal to noise ratio corresponding to that. So we can see the in linear regime or in the squeeze limit, the signal to noise ratio is very high. So this is the conclusion. So thank you. Hmm. Actually, in large scale structure, this is done. So in cosmology, so in perturbation theory, okay, so we do that. Actually, so there are some models in of inflation. Okay, so where we define the any field that is the potential field and calculate the bispectrum of that, and calculate the primordial that FNL parameter. Okay, that is done, but here it is done or not, I am not sure. So maybe more expert. Actually, the non-Gaussianity is very high here. I don't know we can do that.
Some authors have already tried this to divide the bispectrum by the combinations of power spectra of these 3K modes with root over of products of power spectra essentially. And it is motivated by the fact that in case of large scale structure or CMB, you can associate an analytical model to that ratio. However, here, because defining a very, basically creating a very well-defined analytical model that can explain the power spectrum, that itself is pretty complicated. And then on top of that, for the bispectrum, it becomes even more. Means there would be various bias parameters which will evolve with time. So people have tried to do that, but they did not try to, let's say, associate any physical quantity with this ratio. So there is papers by Catherine Watkinson. So starting from 2018 onwards, yeah, you can find 2020, 22 as well. They have several papers where they always use this ratio as the basically reduced bispectrum or Q. And they tried to also extract the reionization parameters using this ratio as the observable. What they found that it does not help much compared to just if you were using just power spectrum to constrain the parameters, at least using a Bayesian framework for inference. And my suspicion is that because these are two independent statistics, and when you mix them up, probably we don't. First of all, we don't understand the bispectrum for 21 centimeter well enough to be able to design a appropriate analytical model. Then we can only extract some sort of parameter out of it. Rather doing that means rather taking the ratio when you, if you choose just one statistics and you basically associate one some sort of, you try to associate some physical motivation to some features in that statistic, that actually is much more simpler to interpret in some way. Yeah, that's the present status.
Thank you very much for the explanation. And maybe, I mean, if I may, okay, I will ask those.
Yeah, any other questions? No.
Once again, this is a very nice question. So, did you, by any chance, did you consider the effect of evolution of primordial bispectrum to, say, 21 centimeter observations?
There are, I think, there are efforts to look at what happens to the primordial non-Gaussianity. How does that affect the structure formation, and how does that structure formation affects your source model, and in turn the 21 centimeter bispectrum. But I think that primordial non-Gaussianity would be very mild compared to this non-Gaussianity, which is produced by the IGM physics rather. So we have not checked it explicitly. So I should not answer yes or no to that question. But there are people who I knew that were trying to see it. Yeah. So if somebody can observe the cosmic dark ages, let's say, they are probably in the 21 centimeter bispectrum from that particular phase might have the signature of primordial non-Gaussian. Yes.
Thank you. Thank you very much.
Okay, thanks to all the speakers. Now it's time for lunch.